Hi, my name is Reproduction and I am a PhD student at Delft University of Technology. In this video, I will talk about our study, which is about introducing and utilizing the helper search objectives for search-based crash reproduction. First, let's define crash reproduction. When a user operates a piece of software, it is always possible that he or she makes the software crash. In the crash report, we usually have a stack trace, which indicates the active method calls during the crash happening. Here we can see an example for a reported crash in an open issue tracking system. In this example, in addition to stack trace, we have an extra description representing the scenario in which the crash happened. Writing a test case that reproduces the exact same stack trace by following this scenario can help developers in debugging. Also, this test case can be used later as a regression test to make sure that this bug will not reappear in the next releases. However, this kind of information is usually not available in the reported issues, so writing a crash reproducing test case is a labor-intensive and time-taking task. Also, this task is expensive for companies because, as mentioned by one of our industrial partners, it needs a knowledgeable developer. Several automated approaches have been introduced to automate crash reproduction. These techniques are using various strategies such as search-based software testing, symbolic execution, model checking, and proning. Previous studies compared these techniques and showed that the search-based crash reproduction outperforms other approaches. This approach takes the reported stack trace and the application in which the crash happened as input. It also takes one of the frames in the stack trace as the target frame. Then it tries to generate a test case reproducing the crash from the target frame. As an example, if we set the target frame to 3, this approach generates a test case that reproduces the first 3 frames of the given stack trace. First, it generates an initial population of test cases randomly. Next, it executes the generated test cases and evaluates their distance from reproducing a crash using a fitness function called crash distance. Test cases with the lower distance value will be selected for producing the next generation of tests. First, the selected test cases will be evolved by a single point crossover. Next, the generated offsprings are evolved by a mutation operator. In each mutation, a statement can be either removed, added, or changed. Finally, the new test cases are reinserted into a new population. This iteration will continue until the search process generates a test case with crash distance 0. The execution of the test case with distance 0 leads to the reproduction of the given crash. Now, let's see how fitness function measures the fitness value. Crash distance fitness function contains 3 heuristics: line coverage, exception coverage, and stack trace similarity. In the first heuristic, we produce the control flow graph of the method M0. Then, this heuristic measures the distance of the test's execution path from covering the target line, which is the line number which appears in the outmost line of the given stack trace. This measurement is done by 2 well-known heuristics called approach level and branch distance. After covering the target line, the value of the first heuristic will be 0, so it is time to move to the second heuristic. This heuristic checks if we have a thrown stack trace after covering the target line or not. If the generated test throws the same type of exception as the given one, this heuristic is fulfilled as well, and we move to the third heuristic. Here we know that we have a thrown stack trace after covering the target line, so it's time to compare the other frames of a thrown stack trace by the test with the frames of the given stack trace. If they are the same, the last heuristic is fulfilled and the fitness value will be 0. Despite the considerable achievements by the search process guided by this single fitness function, it still cannot reproduce all of the crashes due to the lack of exploration ability of the search process. One of the solutions for increasing the exploration ability of the search process is multi-objectivization. In this solution, we transfer a single objective optimization problem to a multi-objective one. Multi-objectivization reduces the chance of search process trapping in the local optima. It also increases the diversity of the generated test cases. There are 2 main ways to perform the multi-objectivization: decomposition and using helper objective. In decomposition, we split our single objective into 2 or 3 representative sub-objectives. For instance, assume that we have a single sum scalarization fitness function, and the red points on the vector is our generated solutions. The sum scalarization function maps these values into a linear function and chooses the closest mapped value to 0. However, if we perform a multi-objective optimization on both of the 2 elements in the sum scalarization fitness function, we always have a set of non-dominant solutions. Hence, we keep more solutions for producing the next generation. However, in the second multi-objectivization strategy, we add one or two helper objectives to the existing primary objective. Again, if we look at the graphical interpretation, we can see that the single objective chooses the closest solution to the zero value for the primary objective. In contrast, with the helper objective, we have a set of non-dominant solutions for producing the next generation. The application of the decomposition-based multi-objectivization on crash reproduction, in short demo, has been already studied in a prior article. In this solution, each element in the crash distance is considered as a distinct search objective. The crash reproducing test case has zero value for all of the objectives. However, we know that a multi-objective optimization should have in-conflict search objectives. Otherwise, the exploration ability of the search process will be negatively impacted. But this is not the case in demo. For instance, we know that for having the stack trace similarity, we should first fulfill the first objective, which is the coverage of the line appeared in the outmost frame of the given stack trace. To tackle this limitation, in this study, we introduce MOHO, which adds two helper objectives to the existing crash distance fitness function. The first helper objective is the method sequence diversity. Here we will explain this objective with an example. Assume that we have a class called C2 with 4 callable methods, and we have 3 test cases generated by the search process. Each of these tests contains some of the C2's method calls. First, we encode each of the tests to a binary vector according to their calls to the methods of the class C2. For instance, since test 0 calls methods M0 and M3 of the target class C2, the first and the fourth index of the vector contains 1. In contrast, the second and the third indexes are 0 because this test does not call methods M1 and M2. After encoding all of the test cases in the population, we calculate the dissimilarity of each vector from each other using Hamming distance. The average dissimilarity of each test vector is the fitness value of that test according to this helper objective. We want to make sure that sequences of method calls in the generated test cases are diverse enough. By having diverse method calls, we improve the exploration of the search process. The second helper objective is simply the number of statements of each test case. For instance, test 0 has length 3 because it has only 3 lines. In this objective, a shorter test case is a feature solution. We want to keep the test cases shorter to avoid the bloating effect. We do note that all of these two helper objectives are conflicting with each other. If you want to have a higher diversity of method calls, you will have a longer test case. Because of this conflict, the exploration ability of the search process will improve. To assess MOHO's helper objectives, we implemented 5 well-known multi-objective genetic algorithms from different categories of multi-objective optimization. We compared the results of the best-performing MOHO algorithms against the state-of-the-art approaches: single-objective crash reproduction and crash reproduction using demo. We applied all of these techniques on 124 non-trivial crashes collected from JCrashback, a benchmark for Java crashes. Due to the randomness in search-based algorithms, we repeated each execution for 30 times. We set the time budget to 5 minutes. So in total, our evaluation contains about 200,000 executions that each of them takes 5 minutes to execute. In this study, we tried to answer 3 research questions. The first question is about finding the best multi-objective algorithm for optimizing MOHO objectives. The second one evaluates the impact of MOHO on crash reproduction ratio compared to single objective search and demo. And the last research question analyzes the impact of MOHO on the efficiency of the crash reproduction search process compared to the state-of-the-art. By analyzing the results for research question 1, we can see that SPEA2 is the best multi-objective algorithm for optimizing MOHO in terms of crash reproduction ratio. As we can see in this box plot, on average, SPEA2 has the highest crash reproduction ratio. Also, the lower quartile of SPEA2 is much higher than the other algorithms, which confirms that SPEA2 is more stable for optimizing MOHO. Also, for showing the statistically best performed algorithm, we rank them with Friedman's test. If the p-values obtained from Friedman's test are significant, it means p-values are less than 0.05, we apply pairwise multiple comparison using Conover's post-hoc procedure. To correct the multiple comparison errors, we adjust the p-values from Conover's procedure using Holm-Bonferroni. The result shows that SPEA2 is significantly better than other algorithms statistically. In research question 2, we compared the best performing MOHO against the state-of-the-art in terms of crash reproduction ratio after 1, 2, 3, 4, and 5 minutes interval of the search process. In all of the time intervals, we can see that on average, MOHO has a better crash reproduction ratio. The other interesting observation is in the 4th minute of the search when the lower quartile of the MOHO is improved dramatically to more than 60%. In contrast, we can see that this value is still about 25% for other approaches. Again, it shows that MOHO has a higher crash reproduction ratio in many crashes. So, we looked at the number of crashes that can be reproduced by each algorithm. We can see that in all of the time intervals, the number of crashes reproduced only by MOHO is higher. Let's look at one of those crashes as an example. This crash is reproduced only by MOHO. This stack trace contains 2 frames pointing to 2 methods, useMainStore and a getPlugin. Here, the target method is useMainStore, which does not have any input argument. Hence, to reproduce this crash, the crash reproducing tests generated by the search process should invoke specific methods such as setWiki and setWikiID to set different local variables in the xWikiContext0 object, and then pass this object to the class under test. Only in this situation, the return value by the context provider can throw a null pointer exception in the getPlugin method. MOHO is the only algorithm that can generate such a test case with the specific call sequences. This is because of the exploration ability of this approach. Finally, let's look at the results for research question 3, which compared the consumed time by MOHO for crash reproduction against the state of the art. Again, we see that the average time consumed by MOHO is lower than other algorithms. Also, the higher quartile for MOHO is lower as well. We performed a statistical pairwise comparison of the budget consumption by each of these algorithms. To assess the effect size of differences between algorithms, we use the Varga-Delaunay statistic. We also use the non-parametric Wilcoxon rank sum test with alpha equals to 0.05 for the type 1 error. The results show that there are many crashes that can be reproduced significantly faster by MOHO compared to demo and single objective crash reproduction. However, there are a few corner cases that MOHO requires more time to reproduce the crashes. We manually analyzed these corner cases to identify 2 negative factors in MOHO impacting the efficiency of the search process. The first factor is the extra overhead in calculating the new helper objectives. And the second factor is the misguidance in trivial cases that we don't need method sequence diversity. The implementation of all of the crash reproduction approaches we use in this study is available in Botsing repository. Also, the replication package of this study is openly available in Zenodo and GitHub. Thank you for watching this video. Have a nice virtual ASE and goodbye.